So far that looks good. So welcome back after yeah, an interesting lab session, I guess, on Monday. We still need to talk about a few things. In the lab session, there were some questions regarding, or some insights regarding the VAO and VBO objects or concepts rather. And I'm not sure. Did anyone do the, or any one of the do the second lab already? Finished it somewhat? Or who had any insights or struggles? That's an interesting shape. Okay. Thanks, yes. Did anyone have any insights regarding this on Monday? Or any questions? Anyone who did the lab? The lab was a bit different. Yep. Sorry?
Regarding what?
VBOs and VAOs. So, yeah, please.
I was confused as to how you were sort of make like one part that has one color, like the part that was already here should have one color, and then the rest two triangles that we are supposed to have. Those did not have fill that color or something like it was a color inside of them.
Read my seat.
Right, okay.
Plutselig så skal vi måke taket på brua, så vi fikk ikke lov å gå under det.
But very yeah, okay, we'll perhaps come back there. We'll see how it goes. I just want to get the general concept right, because there seem to be three different ways of how to model it, which came up, I think, somewhere in the middle of the lab. Perhaps that, when we talk about it, perhaps it answers part of your question. We'll see. So again, we recall that I use the board and I position it in the stream, so forgive me at an odd angle. Thank you. Good. So we had two concepts. One was called VAO, vertex area object, right? So that's kind of the index for all possible buffers they can use to draw, you know, in OpenGL, right? So which is processed through the pipeline and then available. And then it manages, that's currently the relationship, one or more vertex buffer objects, VBOs, right? So this was the actual data. This is just for, you know, referencing and opening or enabling the corresponding buffers, and basically just managing the pointers towards the actual buffer. So you can have multiple of those, right? Easily. The question, however, was, the lab showed functionality which we hadn't seen before, and can probably just bring that up for clarification. Hang on. The lab I'm showing you is a variation of that lab, so bear with me if you see some different code. Now it dawns upon me that we probably need to increase it. Right, how do we increase font size in Visual Studio? That seems to become a recurrent pattern here with my favorite.
Control scroll lockbar plus.
Ah, that should work, shouldn't it? There you go. Okay, very nice. Okay, cool. So, the things I want to talk about is, assuming we have the VAOs on display here right now, but the idea is that we can generate a vertex buffer object and obviously bind that so we can actually fill it with data and actually copy data into it, right? So we had, in that particular case, a coordinate system, right? So that's the coordinates that particular vertex should be plotted to, right? So you have the corresponding colors. And then we're held in different arrays, right? So in generally, if I recall correctly, that's 3 components, so 3 X, Y, Z for per vertex and so on, for colors similar. I'm not sure if we represent the alpha channel, but let's assume it's just red, green and blue, RGB. So cool. So the idea is there, okay, we want to copy or prepare the buffer in the first place. In order to do that, we need to initialize it with sufficient size. That implies the size of the coordinates and color buffer. Yeah, please.
In the most recent code, we didn't have a set, so it was only 2 dimensions. How do you switch between 2D and 3D?
You mean with respect to the
vertex buffer only had like
2 dimensions.
X and Y.
Yeah, cool. Yeah, alright. Thanks for that. That was exactly what I needed the update, because I was obviously looking at this. No, the only difference is there that you defined at some stage how many attributes a vertex has, and you do it right here. So that's basically where you indicate, okay, it's the vertex buffer. What's the size? What's the number of elements I need to represent the vertex? Previously it was 2. That would be x, y.
Yeah.
Here we say, well, you know, it's 3. So, and then the type, we don't want to normalize it, and we start from the beginning of the buffer we find. So it's kind of relatively straightforward in OpenGL. Right now, in fact, we are actually doing 3D. We just leave the z-axis untouched, right?
Yeah.
So that's the key idea. But we get a bit more into that today, in fact, right? Because I want to look into transformations, at least the starting point of it. So for the sake of the discussion right now, VBO is secondary, whether you do 1D, 2D, 3D, or 4D, and why or not you do that is a different issue. But what I want to get at is you initialize the buffer and for static drawing, and then we had those 2 function calls here, and that you haven't seen those before. We did it a bit differently on the preceding labs, and people were asking, okay, what's happening here? And it boils down to how the different buffers are organized. Does anyone have any intuition as to how data can be organized in those different VBOs? If you, for example, look at that sample, or if you reflect on that one. Yeah?
You get a vertex, then color, then vertex, then color, then
cool.
vertex, then
Yeah.
color.
Sweet. So it was one possible orientation, and it was actually nicely drawn. Perfect. Perfect. I'm not sure if he has copyright on it, so if he's watching the stream, well, actually, drawing there. And that's still here. And that's the perfect setup. I think that's worthwhile discussing. So the idea is there, you have various options of actually drawing. So again, as I mentioned before, VIO multiple VBOs, right? You can see it here. I'm not sure if the stream can see it. I'll probably block my screen for copyright violation, who knows. Anyway, so, and the second thing you see here is then you have this GL buffer subdata call. And what does it do? Well, it actually suggests that we want to fill the buffer starting from position 0 over the length of coordinate system, so for all coordinates, not color. So nobody cares about color at this stage. And actually the data, right? So which data do you want to populate it with? And then does the same for color. So note here, the only difference here is actually that we have an offset, right? So here we start at the beginning, here we have an offset off-size coordinate system. And then we actually basically submit all the color coordinates afterwards. So we have 3 different models that are reflected here. 1, 2, 3. Which one of those is there? Yeah,
The top one?
the top one, right? So 1. So basically the idea, everything in color is offset or happens after the position information, right? So that's one possible way of modeling this. However, there are 2 other ones. And the second one we talked, this was the one I actually talked most about in the introductory lecture when I talked about strides in particular. It was really about, okay, how do we organize the data in the buffer? Because OpenGL per se doesn't really know what it is. You just put anything in the buffer and consume it somehow in your vertex shader. Get to that as well. But you need to tell OpenGL what it actually means. And the idea was there, okay, we can actually store position and color adjacent to each other, right? So we have a position with a corresponding color, position with a corresponding color. And the major difference there would be that we have this stride parameter that tells us, well, actually, the next position information starts after the color information. So you have an offset of, the number of bytes necessary to represent color, right? So, which would be, if we assume RGB without alpha, it would be 4 bytes per element. So I have a stride of 12 there before we get actually to a second position information and so on. So that's an alternative way of organizing your data. And then the third discussion was, okay, why not have two buffers, right? So why not keep one buffer just for coordinate information and the other one just for color information, right? So we can separate those as well. And so those are the possible options we can be dealing with. So now I would like to have your viewpoint as to which one would be desirable, or what are the individual advantages or disadvantages of those. Any intuitions? So we have three different options, and you can do any of the lab code in any of those three options if you wanted to. Why would or wouldn't you pick one of them?
Just a pure guess, but
Yep.
you could probably, in the last one,
Yeah.
could handle or kind of multi-thread it, couldn't you? So you had the positions and color being calculated at the same time? Or would that be impossible since
Right.
it's open
Okay.
tail?
Okay. That's a interesting point. Yes. So you could possibly deal with one vertex while the other one is not dealt with. Yeah, but the issue is that at this stage the information is actually submitted to the GPU already. So afterwards you can't do well. You can modify it, but you need to wait until redrawn. Fundamentally, you need, for OpenGL perspective, I could imagine that there's performance advantages here or there, but fundamentally you would want to think about it single-threaded, because you define when you draw and then you swap the screen, so it may or may not involve both of them. So, but it could be the same here. You may just want to draw position as opposed to color, right? So you have the same here, but this is a possible pathway. Anyone? There was some. No. Yeah. Good point. What other points? Yeah.
If it's a large object, then it might be easier to see what vertex has what color in the second one as opposed to at least the first one, because in the first one you would think that, okay, from there it's like 3 steps, and then you have to count to the midpoint and then 3 steps.
So you need to get the relative position suggesting, right? So it may be kind of inefficient, okay? Yeah.
No, not power inefficient, but easier to read.
Easier. So as a developer, you mean?
Yeah.
Right. Okay. Maintainability.
Yeah.
That's your point. Okay. Yeah. Okay. So another point. Yeah. Anyone else?
In the second one, you can more easily add more vertices.
Mm-hmm. You mean this one here, right?
Oh, well, the third one too, but...
Oh, and the third one too. That's right, right? So
Comparatively to the first one.
that's right, that's right. You're kind of constrained, right? You would need to repopulate or reinitialize everything and then overwrite. That's right. So it's quite a bit easier. The idea is basically there is not necessarily a distinct advantage for one of them, especially not with what we are doing right now. But it probably boils down to what you said, which is maintainability. So which one of those approaches is the easiest to maintain? And you could suggest the same by arguing, okay, actually I want to be flexible for all my labs, so I have a template that prepares my VBO setup, if you like, and then you could pick either one of them, and you would probably have a bit more flexibility in those two variants here. So the discussion we had there was, what's the desirable way? And I found more often than not that people actually use the third way. So they actually have dedicated vertex buffer objects for different types of objects in a way, right? For different classes in a way. So coordinate as opposed to color, and then swap between the buffers and actually just read from them selectively. So that seems to be a commonly used option. The only constraint there is the number of vertex buffer objects your VAO can manage. And this is implementation dependent, on your driver/hardware, if you like. I forgot the parameter name right now. It's I would need to look it up. Anyway, you can just inquire it from your OpenGL implementation, and it will tell you how many buffer objects you can actually create. It's generally 16. So, and then you can use those to manage all your vertex-related information independently. So there's different pathways, and that's probably worthwhile exploring all of them. And I think the intuitions that you shared here were quite helpful. You also can go the further road. You can actually have multiple vertex array objects and switch between those. So you may recall when we created vertex array objects, we did something like, let's see if I find this piece of code. It's a bit messy. I just used the lab that we have right now, so didn't really clean it up properly. But here they go. If you create a VAO, you can actually bind it, right? So you could actually initialize multiple as done here for that particular example. So you create two ones and use them independently. So it's one option as well. It's handy if you don't have access to the original vertex area object, or you don't want to affect the code involved in this one. So in this case, I just wanted to have a separate independent structure, basically, so you can do that as well. But this is probably the most inefficient way of doing things. So ideally, especially if you're only dealing with one or two sets of information, meaning coordinates or position and color, it's straightforward to just stick to one vertex area object and have the corresponding VBOs set up there. I just want to, the only thing I actually want to get across here right now, probably we can explore performance at some later stage, because that would be an interesting exercise. I just want to ensure that you guys are clear that there's no single way, right? There's no single silver bullet. So if you see various approaches, you should reflect, okay, which route did we take just now, right? Because some people were confused by the second lab because it actually went down this road, whereas in the lecture we talked about this way of doing things. But for your lab, it probably would be worthwhile also to explore the third option. So have two independent, so one VIO, two vertex buffer objects, and then use them selectively for whatever you want to represent in there. So it could be quite straightforward. Somewhat clear? Different option. Thoughts? No?
Within a buffer, you have to draw them always the same way, sort of like if you have one object that is, say, a triangle with three, and you want that to have no fill color, sort of, and then you have another that has a fill color. Would you have to draw them separately then?
Yeah, the issue is mostly how vertex, it boils down to the vertex shader. And in the vertex shader, you could control that to some extent, because it's an algorithmic way of identifying whether a object or some sort of a primitive should be filled or not filled, then you can do it in code, right? So if you can say, for example, every second one is not to be filled, that's fine. Then you wouldn't need to express that in the shader then, though. Because by default, the shader would assume that each vertex has one color associated with it, right? So you have this one-to-one association, if you like, which we conveniently don't. I'll show you brief an example of, for example, here. If you have a simple coordinate system of, x, y, z axis right now, whatever it means, and you would need to associate one color by default, one color with each vertex to do that. If you find some other way of automatically, calculating the color in the vertex shader, that's fine, right? So or suppress it entirely. In this case, it wouldn't be drawn in a corresponding color. That's right. So you're not necessarily forced to have uniform structural elements in there, but you need to find a way of expressing this variation in the shader itself, because that fundamentally consumes what you produce. So if I just bring up the vertex shader, bear with me, it looks a bit more complex than it should be, but fundamentally what you see here is that you, just comment that one, So is that the assumption is that you get an input for position here, and you get an input for color here, right? So, and then you can, in your main function, you can do some, activities perhaps, suppress or change the color depending on the nature of the position, or so those kind of things. Or if you had a global variable that you can use, so that's those uniform ones, they are specified from C++ code. You could query those ones and build your algorithm around that idea. So it would be the thought. If you can express it somehow in your vertex shader, you'll be fine. Otherwise, you kind of tie down to a uniform representation. It would be the easier way. In fact, in this case, you probably would pick a color that's fully transparent. So basically, you don't have any actual color, and just print it in a synchronous fashion. This way, your code retains also maintainability, right? Because you know the buffer structure and don't have variation in that. But what I want to get across here is that it's really up to you, fundamentally. If you manage somehow to only use calendar every second vertex, that's fine, perfectly fine. OpenGL doesn't know anything about the structure, per se, about the structure of the buffers. You can put anything in there. You just need to tell it eventually what it means, right? So you have some input information coming in, and you need to produce some outputs. For example, GL position means whatever I computed here will be a vertex information that you need to plot on the screen ultimately, right? So, but how you arrive at this, it's basically, this is at best a helper structure. If you find other ways of doing that, it's all up to you. Yeah. So it's not hard-coded that you need to have necessarily even positional information in there at all. Perhaps you only have color in there and generate the positions here by using other means, randomly, for example. Yeah. So but we'll see more of that in the later stages anyway, when we have more variation. But I think from a semantic and maintainability point of view, would be a good candidate to think about perhaps managing those different objects in different vertex buffer objects. So you can switch between those and selectively print them based on whatever decision. Because this is something you would manage in the CPU. So if you go to the display function, for example, here you would have the flexibility of actually enabling particular vertex area attributes, and then drawing them, and then disabling them as enabling another one, drawing those ones, and disabling them again. So it's up to you how many vertex area attributes, meaning how many elements you actually access as part of your in your draw method. Because in the end, it only matters that you eventually will display the drawn or filled buffer, right? The display buffer. Once you're done with all your drawing of your different elements and primitives from different VBOs, you just need to swap the screen and suddenly everything appears. How many you use and which order you use is really up to you. So that's something you need to define. I think it's worthwhile to play around with this more anyway, which we will, if we need to in fact. Yeah. So for example, what I did here is, I get back to that example perhaps later a bit. I basically have two display functions because I wanted to have an entire separate structure for plotting coordinates. And the idea is here I could execute those in sequence and only then show the result, the rendered result. In this case, I'm drawing a simple triangle. In this case, I'm drawing lines. But I want to display them together, so I just execute both of those functions first before actually swapping the buffer, so I see everything in one display. Yeah, so how you manage this doesn't really matter. But we get to that a bit later. So much about vertex buffer for now, just to ensure that you all have that conceptual view somewhat in mind. Eventually, it should come back to my machine here. There you go. So, some other things before I forget that, because I always forget those things. There were the first inquiries regarding the exam. Again, remember the exam for this course, the take-home exam. How many hours does it take? People know it already. Okay, I also would have bumped it up to, I don't know, 150. No, it's 72 indeed. So it's quite should be quite manageable. How many of you did the take-home exam before in other courses? I think the rapid prototyping people implicitly did take-home exams more or less, but it's somewhat similar in a different way. So the question, however, is what time works better for you? Because there were people that were worried about their exam timing and clashes and so on, and we don't have those issues. We are relatively flexible in defining when we want to do it. So it's not something you need to decide now, but something you check your calendar once come home, get home and so on, and see what works better for you. We'll see what the resonance is in the class. We probably go majority-based voting here. But I looked at the general allocation of exams. They're usually a tad later than that one. So the question is just, do you want to do it immediately after the last lecture? So you're pretty much done after the course. It just means you put in a lot of effort and hone your skills immediately after the course ends, which is probably kind of reasonable, I guess. Or perhaps do you want to have week in between. So you can actually have a week of, you know, reflection and learning more and so on. But on the other hand, the take-home exam, part of the exercise is actually to learn, right, on the fly. So it's not so much you study for it, it's opposed to getting the exercise and, you know, dealing with this and learn heavily for 3 days, right? Ultimately, you will learn for 3 days, but I wouldn't invest the full 3 days in just learning. You probably need to do something as well. So it shouldn't actually hurt doing it immediately after last lecture unless there are other conflicting obligations. But I would like to fix that at some stage reasonably soon, perhaps end of next week, so Friday, perhaps we can talk about this again. I hope the stream people got that information as well and can think about this. Cool. So one other thing I wanted to get out today was the assignment, but last night when preparing the slides for today, I realized it was 3 o'clock in the morning, so I gave up on specifying the assignment, so I was a bit admittedly late on that. So I bring it in on Monday, and then we'll define it. It will be quite straightforward. It will be 2D, not much magic. I just want everyone to, you know, get their hands going and brains and actually start coding in OpenGL, right? So we have something going and then can move to something more advanced. So it won't be terribly complicated, but I would have liked to talk about it already, but my bad. So on Monday. Cool. So the actual topic I wanted to talk about, so this was part of it, this organizational aspect, this organizational aspect and then this organizational aspect. The other thing is that to get a bit closer to the idea of transformations, because they're quite important in drawing. And we have addressed them, I think, reasonably intuitively. I just want to give you a brief picture overview of what it involves. But before they do that, again, terminology session. So some terms we need to entrench, so you guys interact on that basis, use those terms, and if you hear those terms, you actually understand what's meant and so on. So of course, we don't have a knowledge-based assessment per se, meaning we don't have a written exam, but still it's probably worthwhile to know what those concepts mean and what they are, what they entail. So let's bear that in mind. So first of all, we have basically vertex data is quite important. It's all the information you need. I put the slides up anyway. That you need in order to draw an object. So that's the kind of important aspect. We have a per vertex representation that was particularly important for vertex shaders. What were vertex shaders again? Too easy or too hard? Come on. I hope we're on the too easy side here right now. Did I talk about vertex shaders? No, I didn't, right?
Shading of vertexes.
Exactly, right? So all the given input vertices, right? So they are basically rendered by or handled by the vertex shader. At least there are potential input, whether they actually plotted or printed, different problem, right? So yeah, that's right. That's the vertex shader deals with this one. And then there was a later stage of the pipeline, we talked about rasterization. The idea is that we're converting whatever structure, geometric elements we have, triangles, into pixels, right? That are actually printed and plotted on your screen according to your screen resolution, your zoom level, and whatever else for K features you have on your fancy monitor, right? So let's dealing with this one. Fundamentally, it's just an array basically, right? So of the plotted value. So if we talk about pixel data, then it becomes more relevant to talk about aspects such as colors and lighting. We didn't talk about lighting yet, but colors is something we touched on already. And we recall where are colors, particular for non-vertex pixels, say with care, managed in OpenGL? Fragment shader, right? So it's something we, again, recall the pipeline concept. We need to pass that through the vertex shader and actually to use it in the fragment shader, right? So that's where colors come into play. So it's closer to the rasterization idea already at this stage. Cool, so we didn't talk about this yet, so I wouldn't want to push that right now. So pixel operations basically is precisely what the shaders are doing, operating on any incoming information, and fragment shaders and the frame buffer is basically what you fill before you actually switch between the front or back buffer in order to display it on the screen, right? So just be mindful of some of those terms. Anyway, shouldn't be too much complication there. So one of the core concepts that we're using when drawing, and in fact for any sort of complex structure that we're dealing with, is always a basically triangle, right? So we can decompose nearly any structure into some sort of triangular fashion and represent different properties. So obviously you have vertices, individual points, or lines. That is basically a collection of vertices on each referred to, or a face or plane if we have a three-dimensional space we can deal with. And part of the reason it's used is that it's relatively fast and easy mathematically to transform them, right? Both in position, direction, or across all angles in 3 dimensions, for example. And that is part of the reason that it's so so useful, because it's easily managed both in hardware and in software, and that's something we probably do most of the time here anyway. We talk about projection afterwards. So this is pretty much the processing that we need to be aware of, and the fundamentals that are associated with doing that. So we model pretty much all the objects that we interact with and display on the screen in the form of triangles or vertices, so some sort of geometric primitives that we have. And we do that using object-specific local coordinates, right? So if you, for example, render a cube, you will render the cube, for example, centered in 0, 0, 0, and then X, Y, and Z, and then think about, okay, how could I actually render the individual faces of the cube, right? So by moving towards the Z-axis, which is moving outwards from the picture, or towards the Y-axis, upwards, or X-axis. And you basically construct your, and now it's come my drawing skills into play, which are next to non-existing. I tried nevertheless. Oh, there you go, we get somewhere. So you basically center the, let's do a different color, center the object. You don't need to though, that's pretty much up to you, but that's often how it's done. You center the object around the 0 coordinate, right? And which is in principle fine. We'll get to that in a second, why it's important to be aware of this one. So you need to define how you actually model some cube or whatever else, and it's quite straightforward. By the way, how many triangles do we need to model a cube?
12.
Why? Yeah?
Because 2 for each side.
Yeah, that's right. Any questions? No? Easy, right? Good. Good, yeah. So 12 triangles to model the corresponding faces. So, and this brings us back to actually how do we think about models, right? So if we decompose models into triangles, then as you said, we have actually kind of a uniform structure we're dealing with, especially with the cube and with fixed dimensions. We basically have a representation of the individual triangles that we need to just orient and organize to produce those objects. What's another example for a more complex object that we probably represent as gamers?
Characters.
For example, right? Yeah. So characters, or what else are we dealing with?
Landscape.
Landscape, yep. Landscape's good. Landscape is tricky, yeah. Let's not do landscape, but no, actually, landscape is fine as well. But anything. So, for example, I have a nice example of a car here. I found you basically decompose your entire model into various components. Not as simple as triangles in all cases, but they may actually themselves be composed of triangles again. For example, for a car, we are possibly dealing with wheels. Really 2000s that kind of car, right? So nowadays you still have wheels. Anyway, so you have wheels, doors, bumpers, trunks, all that kind of stuff, right? So, and you assemble it pretty much into a coherent whole, but fundamentally you're still dealing with the individual components. And what you model from there is what is called a scene graph. So this is basically just about how to organize all that kind of stuff, all those components to actually reproduce a car from it, right? So for a car, we know we have a hood, trunk, front bumper, and so on. And we have also uniform structures, for example, the wheels, right? So the only thing, what's the only thing that we actually need to do with the uniform components that we possibly have, for example, doors, or wheels. What's the only thing that's different in that entire model? In object orientation, they would be treated the same, right? So we have 4 instances of wheels, right? Or let's say 5. We may have a backup wheel and a trunk. But from a graphics perspective, we need to think about something else, and that is
lighting.
yeah. Oh, but before that, way before that, look at this thing.
Individually drawing each component.
Yeah, exactly. But what's particular about this? What makes them similar or different?
I mean, you don't have to do the same calculation for each wheel when you calculated what one wheel looks like. You don't have to do it for the 3 others.
Yep, that's number 1. Yeah.
Position and rotation and stuff like that.
Exactly right. So yeah, in contrast, in object orientation, we don't think about those things, but we still think in the model sense. But here it's more like a literal visual model that we need to be dealing with, and we need to do some modification. So yes, we can reuse the calculations to actually identify an individual wheel, right? So to model a wheel centered on the root coordinates, 0 coordinates if you like. But we still need to deal with it afterwards when we compose it into a coherent model. And there's those 3 fundamental operations that we're dealing with, which would be translation, meaning moving a object along x, y, or z axis, right? So in this case would be, I guess, z axis. What's the other one? Rotation, right? So we need to show the opposite face of a tire in this particular case. In fact, we probably wouldn't see that, but in fact we need to turn it. And the last one was scaling it, right? So we need to change the size depending on the perspective, right? So an object further away may appear smaller and so on. That's something. But that's not the core argument. The argument would be, irrespective of whatever size and choice of coordinates you have for your individual model, you want to be able to scale it to the environment, right? So you want to, for example, if you have a tire model, you want to reuse it in 2 different games, and they have different coordinate systems. You want to be able to translate it, or actually rather to scale it according to the properties in the other game, right? So corresponding game. So those are the 3 major operations that we need to do on objects in order to come up with, for example, coherent model. Question? Cool. Right, so that's in summary just those ones, right? Translation, we're moving in the 3-dimensional space. Rotation, we're changing orientation in the 3-dimensional space across possibly all axes, x, y, and z. And scaling, we change size. And probably doesn't really surprise you. What's the kind of operation we need to use to do that? Yes, right? So we need matrix operations in order to, because we need, we want to represent vertices, and we have multiple of them, so we need a matrix. And then if we want to change or do anything coherently to the matrix, like a linear transformation, like increasing something, but retaining all the proportions, for example, and angles and so on, then we need to have some sort of matrix operation doing that. Before we do that, some of the fundamental concepts that we need to be dealing with in order to comprehend this coherently. So we have concept of vectors. Then we need to talk about a bit of trigonometry. Is that the right pronunciation?
Yeah.
Yeah? Okay, trigonometry. Well, how do you pronounce it in Norse?
Trigonometry.
Ah, trigonometry. Okay, I can do that. It's easier. So, and then the matrix operation, as mentioned before, and then we look at the transformations, which obviously are special cases of those ones. Just one word on vectors. So, what are vectors usually used for? What do we use vectors for?
Position.
Position. Yep. Cool.
Translation.
Yep. Translation as well. Yeah. Come there. Yeah. There's some element. What else? But let's not think in a complex sense. But what are the general ways of? Yeah.
It stores multiple values.
Yep. Cool. Yep. So that's right. You could principally use it as a store of multiple variables, right? Think about an array, right? So as a vector, if you like. But generally, we make an assumption about the structure of the vector, right? So, for example, x, y, and z is a certain assumption that we make, right? Because we have a fixed association, so we can actually do matrix operation on the corresponding elements, right? So on the x element, y or z element. So ordering is kind of important in that context. But in addition to coordinates, what else do we represent? Think physics, perhaps? Velocity, yeah. Yeah, but you're on the right track.
Acceleration, forces.
Yeah, right, yes. So, and fundamentally, that is Directions, right? So that's what I want to get. But it's fundamentally the same thing, right? Because we represent the direction of force in a given direction in physics. So those are two kind of things we need to be dealing with. And point is, since we're modeling 3D here, we also have physics involved, right? So we need to bear in mind that vertices rather can be used, or vectors rather, sorry, can be used to represent exactly both of those, right? We want to be able to represent both points, coordinates, as well as directions as well, right? For movement and so on. So that's the base direction, base idea. And in order to differentiate those two ones, we need to have what's referred to as a homogeneous coordinate system, or homogeneous coordinates, because just using three-dimensional vectors, right, to represent x, y, z, is not enough to differentiate, at least for now, between a point and a direction, right? So we need to keep them separated, so we possibly can calculate a point from another point plus direction, and so on. Okay? That makes sense? So we want to ideally be able to use both characteristics. So if you have a point in space, that is most certainly not visible on the screen, and then we have another vector representing direction, we want to be able to calculate this new point, right? So that's one of the key ideas, but it has some other purposes as well. But for now, I just want to introduce you to the convention that I use to manage that. And fundamentally, it's about introducing a fourth dimension, which doesn't do anything else right now, other than just keeping track of whether it's actually a coordinate or point, if you like, or a direction. And to do that, we have this W element. So we're x, y, z, W. And we'll see that W element again when we talk about rotations eventually. And the idea is that if W is equals to 1, it represents a coordinate. If it's 0, it means it's a direction. So this solves our problem, because now we have a uniform representation, unambiguous representation that captures all those two concepts, in fact, that are relevant for us. Yeah. So far, so far, no magic. It's just a matter of convention, I guess. Cool. So looking at the matrix transformation that we're dealing with, there's quite a number of them, and generally it involves using some sort of base vector. For example, you position in space. That's a classical thing, vertex shader, operation on a particular vertex, and then some sort of modification, some transformation matrix that affords a particular change. For example, translation. If we, for example, have a translation matrix, we have a shift to a particular direction, where scaling is retaining the origin but changing the size. Note that in the case of translation, we're actually changing the origin. So it's not so much, one of the key differences there is that we're actually moving an object to a different location, but retaining its original size. Whereas in the scaling examples, we actually retaining the origin, but just changing the size of the object. So it's a slightly different operation there. And then there's obviously the rotation bit. So it's the tricky one. So we want to be able to rotate it across the x-axis. Let's try that one. So across the x-axis, y-axis, or possibly the z-axis, right? So those are the three axes we're dealing with. We can get to that in a second, how to do that. Like shearing is only changing a operating on one particular dimension to produce a shift, or in multiple, for example, 2 dimensions, to have a kind of a stretch plane projection in 1 or 2 that only affects 1 or 2 dimensions, for example. We're not dealing with this today. And obviously the idea of reflection. So it's the reflected representation of the original object that you're dealing with. So those are possible transformations we're dealing with. The most important ones, however, will be translation, rotation, and scaling. And we'll briefly talk about this now, how to actually do that, and come back to the other ones when needed. Plus, you'll be able to pretty much do it on your own anyway, because even though I'm talking about all of this, it actually will not challenge you, because it's all available in the GLM library, right? So that's the default library to maths on OpenGL, or de facto standard pretty much. Or does anyone know another library that's commonly used? I know some of you did some OpenGLing before. No, cool. Yeah, so GLM, and basically there are functions for all of those, so it's not really magic, but still worthwhile talking about this briefly. And the idea of matrix multiplication, as you probably know from high school, and that zooming didn't really help my course here, did it? It looks a bit pixelized. So it's basically that you multiply each row by each column of a given vector, right? If you do that operation and then sum the corresponding results, that's pretty much the idea. So in this case, we would have a multiplication of those two ones, followed by a multiplication of what am I missing here? Yeah, so multiplication of those two ones, then multiplication of those two ones, multiplication of those two ones, and adding those up. So you have again resulting elements would be a vector again as opposed to a matrix. And if you do that with matrices, you do it across across both matrices. So basically multiply row with column and then add them up within the elements. I'll show you an example in a second. The only thing that's important to bear in mind that the order of the operation matters in the case of this multiplication. So it's quite worthwhile to bear that in mind. Looking at a specific transformation, we always deal with some sort of translation matrix that we want to multiply an origin with, or an original coordinate with, a vector, in order to afford some changes. And those are the only things that are actually relevant to do that. For example, the translation matrix that affords a change in x, y, or z direction would have the following pattern. So the offset would be substituted for the corresponding variable value here. So if we have, for example, an offset by 10 in the x-axis, and we would multiply those ones, so we would arrive at, well, surprise, surprise, as a vector representing 20 and leaving all the other components of the vector untouched, right? Because they would basically be resolving to the same value, because we have a identity reflection on the y-axis here for 10. In all other cases, the elements would be 0, therefore the resulting sum of those would be 10 and not affected. So that would be a translation matrix. The function to use that in OpenGL would be in the GLM library, the GLM translate function that takes some matrix as input and then applies this operation that you specify here. So in this case, for example, we're specifying a three-dimensional vector that is pretty much this vector here. That suggests what kind of translation you want to perform. Do you want to do it, in this case we have a shift by 10 on the x-axis, leave the other axis untouched. Once you have that one, then you have this matrix over here, and you can then multiply it with your individual vector. So assuming you have the given input vector, which corresponds to that one, you perform a matrix multiplication, or the multiplication of both of those, in order to get a transformation of your original vector, right? So, meaning you can keep this transformation matrix for whenever you actually need it, so you don't, in this case, you can just keep track of it and use it whenever you need, on how many objects you will need to use it on. What did I want to say? Is there anything else I need to mention? Yes, the only thing that you probably need to bear in mind that the order of execution is essential. So we need to be keeping track of this one throughout all the operations. That's the most important bit. So in this case, we would have the vector times matrix operation. That's right. So the second transformation operation, which is also super straightforward, is the scaling matrix. Note that the difference is basically just here on this axis, because it basically represents what's the multiplicative factor that is applied to the individual axes. Right? So if we, for example, want to scale a vector by a factor 2 across all different dimensions, as done here, or across only one dimension, so we only expand the z dimension of a given input vector, we can do that. Same operational principle. So we multiply the individual elements, and form the sum of those and arrive then, in this case, at a a resized original vector. But note that again, as I mentioned before, the origin per se is unchanged, right? So it's just scaling up, but it's not changing the actual location in space. In GLM or in C++, so the GLM library is used in C++, so it's not directly, in this case, not directly operating on the GPU, but rather in your CPU code. It would be as simple as that. So you basically have the scaling matrix, which you need to indicate, in which you need to indicate what you want to actually do and which dimension you want to resize, and then multiply that with your original vector. No magic there. No? Straightforward, right? Cool. So the last one we want to talk about in some brief way is the idea of rotation. And so rotation is a tad more involved. We basically need to look back into angles, right? So how to represent those ones. And we'll find actually that the rotations are basically rotation matrices for particular axes are represented in this way, that we have cosinus and sinus functions that do the conversion. And just to get an understanding of how that actually happens, we can probably elaborate this on the board, or at least attempt to. But first, good. So we're not using.
I think the brakes are on.
Yeah, I know. That's right. I agree. I don't have a. There you go. That would be helpful. What's the time right now? It's 11. Do you want to have a few minutes break, reasonably? Yeah. Sure. I'll give you 6 minutes break, so meaning until 11:15, if that works. Cool. Cheers.
Det er litt senere, fordi han driver og måker på brua der borte. Så jeg fikk beskjed.